With refraction, the location of the image can differ from the location of the object. For instance, in this example here, you can see that the image of the pencil seen in the glass is different than the actual location. We know that this pencil is continuous and the pencil must actually continue along this line, but it looks like it's slightly shifted. So what we're going to do is take a look and see if we can figure out where the image is located beneath the surface of a water pool. In order to figure out where the image is located, it comes down to tracing the rays back, the rays that are emerging into air, and seeing where it looks like they came from. So one of the first questions we need to ask is, do all of those rays appear to come from the same location? If they do come from the same location, then everybody will agree that the image is located in the same place. Now, as it turns out, the location of that image does change depending on what sort of angle you're looking down into the water at. You see one image location looking straight down compared to looking at an angle and looking at an even steeper angle, you see a slightly different location. So there really is no one point where the image is located. The image location depends on where you are. So what I'm going to do is try to derive an equation that relates the apparent depth, how far beneath the surface the fish looks like it's supposed to be, compared to the angle theta 1. In other words, that's the direction of the light ray that's leaving the fish. And that will then allow us to figure out where that image is located. So the first thing I need to do is find a way to relate this horizontal distance where the light actually emerges from the water or strikes the water's surface. So I need to find a way to relate this distance x1 to the angle of light leaving the fish. Once we've done that, we can then also relate theta 1 and theta 2. Once we have that relationship, then I can go ahead and track back where it looks like that light ray originated from, and that will give me a location for the image. So first, in finding a relationship between x1 and theta 1, well, this is nothing more than a little bit of trig, where my triangle is this part right here. If this is my angle, then the tangent of that angle is going to be opposite over hypotenuse, x1 over h, or x1 is simply equal to h tan theta 1. Next, I'm going to relate these two angles to one another, and this is simply Snell's law. So solving Snell's law for theta 2, I end up getting this equation right here, where we have the inverse sine of n2 over n1 times the sine of theta 1. Now, in order to find the apparent depth, what I'm going to do is track this light ray back to where it intersects the x equals 0 point. So just tracing that back and figuring out what this depth is. Well, again, we're just dealing with triangles, so this triangle right here has a tangent of x1 over d, and the other thing to notice is that all of these angles are actually just theta 2. So it turns out that x1 over d is tan theta 2. Solving that for my apparent depth, I get d is x1 over tan theta 2. Now, I already found an equation for x1 and for theta 2. All I need to do now is go ahead and plug those into the equation. And there you have it. Now, I will admit it doesn't look very helpful right off the bat. What I'm going to do is go into CoCalc and actually plot this and see what we see in that situation. So what I've done is gone ahead and typed in my equation for d that I just derived, and then I went ahead and plotted it. And so here you can see the curve. So theta equals 0, that corresponds to looking straight down. And so looking straight down, the apparent depth is going to be somewhere about 0.75, where I've set my actual depth to be 1 unit, 1 meter, 1 foot, whatever units we're using. Now what we'll see is that the farther out you get, in other words, the larger the angle that you're looking down, that the apparent depth gets smaller and smaller and smaller and smaller until you reach a certain point. Now what happens when we reach this point right here, this is where internal reflection, total internal reflection, starts to occur. And so for any larger angles, we're not actually going to see anything. It's going to be just a complete and utter mirror. And so here we get a apparent depth of probably about 0.35 as the minimum. Again, the actual depth is 1, and the apparent depth is somewhere between 0.35 and 0.75.